Hello learners, welcome back again. In the series of SiEPIC EBeam PDK, we are trying to learn with demonstration the different components available in this process design kit. So in last three episodes, we could understand as well as demonstrated the working principle and characteristics of adiabatic coupler, then brake grating, and followed by broadband directional coupler as well as directional coupler also we have done. So today we shall try to cover this fourth number, that is the crossing. So let us see what is this crossing, which is given on this page number. This is broadband and it is moving fast. Let me check slowly. Yeah, this is the crossing. So as far as its description is concerned, crossings are used to support the routing of more complex photonic circuit. So basically this is used for routing purpose in the photonic circuit. Improvements to the waveguides transmission can be achieved by reducing diffraction that occurs in the component's center crossing region. So this is the center crossing region. To widen the waveguide core, elliptical mode expanders are used for this component. So here elliptical mode expanders are used in order to widen the waveguide core. So model name given in SiEPIC EBeam PDK available in K layout is this EBeam underscore crossing 4. 4 indicates here there are 4 ports. And compact model information is given like it supports for both TE mode as well as TM mode light polarization. The specification of this crossing has been optimized at the operating wavelength of 5050 nanometer. So far as performance is concerned, transmission loss is less than 0.2 dB and crosstalk and reflection is less than 40 dB in broad bandwidth of 20 nanometer. So this circuit was implemented, or this component was implemented by Vichy in 2011 based on his article highly efficient crossing structures for silicon on oscillator waveguide. So let us see what further information is given here. Similarly fabricated by OPSIS and published with test results in a article titled a CMOS compatible low loss and low crosstalk silicon waveguide crossing. So in figure 2 you can see this is the optical micrograph picture of crossing. So these are the different ports and this is the central mixing area. Parameters not applicable, simulation and experimental result not tested with electron beam lithography. However, another researcher, P. Sanchez et al., has demonstrated this characteristics from 1.54 micrometer to 1.56 micrometer. The transmission loss characteristic is like this. So person has simulated this crossing with 3D FDDT method and experimental results are like this, fluctuating. So additional details, potential use you can find in some of the applications are here. Like it can be used as 2x2 splitter combiner, the way we have seen coupler, broadband national coupler with adjustable coupling coefficients. Ring regulator, it can be used in ring regulator, it can be used in Mach-Zehnder interferometer. Our references are here. Number one, P. Sanchez et al. Highly efficient crossing structure for silicon on insulator waveguide. Optics letter, volume number 34. Number 18, pages are 27602 to 2762, and it was published in 2009. Another article by Yi Zhang, Shu Yu Yang, and Yu Zin Lim, Zhao Qian Lo, Christophe Galland, Tom Herjen, and Michael Hochberg, who is the again the co-author of the book Silicon Photonics with Professor Lucas. So the title of article is a compact and low loss Y junction for some micron silicon waveguide. It was published in Optics Express. Through this Optics Express, we can uh, download article freely. However, it was not freely available through Optic letters, and I was not able to download through our NEHU. This one also Vichy article, which is also get published in Optica. Yeah. Okay. So this is what is mentioned in the PDK. So we can further move ahead to see how can we use this crossing. So I will stop sharing this screen, go to the K layout as usual. No, K layout. So you can see this is the K layout I have opened. Now I will go to file. In this new layout, I will give top cell name as here crossing, and you can give SCA. Today is 24 January. Okay. So new layout is visible. So let us first draw floor plan. Go to box. Draw this rectangle. Escape. Click. Press Q. Object properties has come. Now 0 here, 0 and 605 and 410 as given in Lucas course. Press F here in the middle. So with this, now we select this EBeam component library, and before that go for this material silicon instance. We select EBeam grating coupler for the connection purpose. So here now we can take 4 because 4 ports are there. So this is a grating coupler TE mode. I will take another one also TE for TM mode also. But first one is TE. Say OK. Go to instance array. Then I will take 4 and putting here. So you can see within the given area we can connect 4 grating coupler. Click here, press escape, go to display, press full hierarchy. Okay, at the same time let me take TM mode 1 also, grating coupler. This is TM mode grating coupler, and 4, this should be 4, and so orientation needs to be also changed. Before that, 4, rotation angle 180 degree. So we can see here, both sets are available now. After that, I will take this crossing. So here we can see crossing is available here. Say okay. 0 degree. And crossing I can put here because 1 should be the laser and 3 should be the output. So I will put here 1 crossing. And another crossing put here. Press escape. You can see crossing size is so small. This is the crossing, and here you can see. Now press F. Actually, by mistake, there were 7, I think. So I will select this. Press Q. Instead of 7, it should be 4. So yeah, now it's okay. Press F. So let us make now connections. Select material as it is silicon. Go to path, 0.5 micrometer width. And this will be your laser source. So I will give here. Connection. 1 input and 3 output. Let us see what kind of output we are getting here. So double click, press F, go to SiEPIC, path to waveguide. It is asking here this waveguide width. Yeah, that is okay here. But whenever I am going to connect TM mode, I have to put this radius 10 micrometer instead of 5 micrometer. So say okay here right now. So connection is made. Now go for the other connections. So let me take this output as here. Go to this one, and this one from here to here. Double click, and this will be last output. Let us see here. It is going to connect. Yeah, and I will go for SiEPIC waveguide, path to waveguide, and all connection has been made. So I hope you are able to see. So now going for another one. But before that, let us save it. It should ask name. So here, layout design. I will open another folder, new, the name of crossing, 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 and today is 24th Jan. Put here, and now I will give name here, crossing EB, both for TE and TM mode, 24th Jan. This is the GDS layout which we are saving here. Now I will label the text. Okay, before that, yeah, the connection is made here. Yeah, connection is made. I want to now labeling text. Go for this OPT here. Instead of break grating, it will be now crossing. E mode and 1550. So text. Okay, let me further. Actually, date was wrong. So it is today 24. 24. So here I will put OPT pin at the center. It is done here. Press F. Okay, so this is save again. Now going to make connection to the TM node, light propagation. So for that, as you know, radius should be, bending radius should be 10 micrometer minimum. So go to path, 0.5, okay. Now this will be your input. So it is about 19. Let it be here and coming this side. And this side here. And go to SiEPIC path to waveguide. Actually, it has not asked. So bending radius is still, I hope it is 5, so which is not correct. So skip. So I have to do something. How to? Okay. Press Q. Cell parameter. So radius should be 10 micrometer. Okay. F. I think I have to go this path 0.5 recent basic path is okay. Then this should be here up connection. This should be output number 1 here. Go to waveguide, path to waveguide, Q. Let us see whether it is radius 5. Let us make it 10. Press F. Now another connection, this to this. Zoom in to bring it near to. Go to SiEPIC waveguide, path to waveguide. Connection is made. Q cell parameter, that radius 10. Okay, so F, and now last connection can make from here. F, go to here, go to here, and here to it, double click, SiEPIC waveguide, path to waveguide. This is F, yeah, Q, cell parameter, and I hope this is this one. Q cell parameter 10. This already cell parameter 10 radius, and this cell parameter 10. And now let us label it. Yeah, Q this text. So now it is TM instead of TE. This TM crossing. So I will put laser here. Okay, one more thing I have to do. Can I flip it? Text. It's basic editing. Okay, I will put here only. Q. Skip F. I think left hand side TE mode light and right hand side TM mode light propagation. Now save it. So last step is to put lasers. Go to the SiEPIC journal. So laser will be here. So this is interconnect laser 1 and PC cell. So TE1 and for TM it is 2. So 1500 to 1600 nanometer. And okay, at a time I will do one simulation. Then now detector. So detector number 1. Okay, so this is detector number 1. Let us see, this is detector number 2. This is 1 and this is 2 and this is 3. Skip. So this is 2. Q, rename it 2, and this Q, rename it 3. So these are the 3 outputs. So we have done here. So press save. Now let us go for functional check. So tool layout error as usual. This is about labeling only T mode TM. Others are okay. So press F. So you can see our circuit is ready. Go for SiEPIC. This circuit. Okay, so till it is opening, let me revise it what we are doing. Stop presenting. In between, I would like to just share one more thing, that people should use this GitHub desktop platform, where you can see this SiEPIC tool is saved as repository. So here all updates are being fetched. So 9 minutes ago this update has been done. So here these are the things which is keep updating. So I have also SiEPIC EBeam PDK. So latest update was done on 17 January 2022. So this is how. So from here you need not to download always, you just have to symbolic link, you have to create and update on regular basis. So this is uh, other things are also here. Let us see, like K layout also used to update on regular basis. So it is hanging on. So you can see 6 days before this merge pull request was done. So this is shared basis contribution. So I pick again, I'm showing here. So let me check my simulation is ready. It is still opening. So I will stop it. I want to show you again what we are trying to do. This is our K layout. So you can see left hand side we have created this. Okay, so text also we can write here. Use text. This, and here you can see I can write crossing simulation in TE mode. So I can put its size, say 5. I will be very big, so let it be 4. And I can put here for my understanding purpose, press F. Okay, this here. And similarly at right hand side, okay, this is for TM mode. TM mode. I can put here, this is for TM mode. So this kind of labeling we can do. Further we can see these are the inputs and these are the outputs. Okay, in between my simulation is ready. I will share now. So as this numerical platform is ready now. So you can see here the compact model of crossing is visible here. If you would like to see what is the inside, you can just right click and expand. So inside this is the circuit, complex circuit. You can align it properly because all labels are put here. How it has been made. So coming back, now go for the simulation. Simulation completed. Now we can plot. So we can go for first, say by default this gain of all 4 outputs. So let us try to see what is it is showing. So display. So you can see, yeah, there these two curves broadly there should be four, but two are merged together. Let me show you one by one. So first one is this blue. This should be say upper photo detector, first one. So first one, so let us see, it should be blue color and 5. So here this is the gain curve. Basically you can see gain is quite high for larger range, so minus although very less. So this is the first one, and then second one I will show you here in between what are these output, so that you should not confuse. Go to window, and we should have this one. So first is this one. This is the input. Laser light is coming to this port. The second one is this up. So directly it is here. Okay. So this is the first. So here you can see uh, output is lesser than green one. So we will see what is that one. So this is first. Second one is this one. So this is the second, and third one is this. Okay, so first, second, and third. These are the three outputs. Okay, and this is the input. So just see in what way. Anti-clockwise we have taken. Sorry, clockwise. So clockwise we have taken. Output has been taken in a clockwise manner. So I will stop sharing. Go to again our result section window, and here it is here. So this is the your first one, as you have seen. This is the first one, clockwise direction. The second one, let us see second one, which is just in front of. So this is the second one, upper, which has more power, straightforward. Okay, whereas it is bending because of the bend, less power. Now third, so third one is again you can see here this. So first and third are giving same. Second one, which is the state one, giving the higher power. Okay, so this is the output. Now let us see wavelength versus transmission. So I will just close it, and let us see how waves are traveling, transmission of the waves. Okay, so I will just select transmission or transmission 2. Transmission 2 is just a straightforward one. These are in adjacent one. Now go display result. Now you can see here. So first one is you can see uh, we have seen left upper. So scale. So this is a transmission. So we go for this. Its absolute square value or all three. Okay. And now this line width. So first upper one you can see here this blue. It means light is almost not going very heavily. It is attenuated. Okay. So this is first one. Second one we can see 5. This is the second state. So cross, and third one red. Okay. So light is just straightforward going. However, very less light is there in the port 1 and 3. In second one it is very large. So okay, so this is the transmission. Okay, I have selected all three, these three outputs. So in nutshell, the light is just passing through the state from this to this, from port 1 to port 2. Stop sharing. Go to window here. When light is coming, it is straightforward passing from this waveguide to this one. And where less light is going in these two, vertical one, horizontal one. So this is the crossing wavelength wise. And however, loss is, yeah, we have seen. So we can see loss curve also instead of gain. So I will remove this. I will go for losses. So 1, 2, 1. Let me show you what I'm doing. Window, this one. So it is being plotted basically. So first, this is the loss, first one, and second input, this is the loss, and third one, this is the loss. Now get plot, display results. So you can see here. So port 1, which is the upper one, we can see here line width. So loss is less, upper one, and below one, state one. I think here our interpretation goes just reverse. It says that you are getting very less loss in port 1. This output is available at higher rate at port 1, which was the upper one, clockwise direction. It means in crossings, light is available. Now, second one, this is state one. So light is very less. Loss is, no, this is loss. This loss is very high. Okay. It means very less light is available. Okay, sorry. Yeah, that is interpretation is okay now. And third one, again here. So straightforward coupling is more compared to uh, compared to vertical direction. So this is the same thing. So this is what we try to say here. Now we can save these results as this in crossing, clear design, and go to crossing here, crossing loss character. Okay, similarly this save as layout crossing. Okay, how much value it is there that one should understand. Let us see, so that we can compare with TE and TA board. So you can see this is the loss, which is very less for green, which is state one, but how much? That is the minus 5.7. No, loss is 5.7 dB, and here it is 44 loss. If you want to see gain curve also, instead of this. Okay, let's plot both loss and gain. So you can see here. So crossing one. So left hand side must be gain, right hand side must be loss. So and these values are expressed in TB and these are the TE mode. So here we can see this is line width. Let us see what it is. 5. Yeah. So this one is the loss characteristics. This and this side is the gain. This side loss, gain, left hand side gain, and right hand side loss. Okay. I think one has to remove, otherwise we will always confuse. So let us remove loss. This is loss. Loss has been removed. And we can see here this is now gain. So gain is minus in minus dB. So it means this is a loss only. And here now we can see this line width. This is the gain. So gain is very less for crossing one. And this is a straight one. So gain is minus one is higher than this one. And here again downward. So this is for TE mode. So we can save this TE mode crossing. Gain curve. Okay. Now we have already saved it, I think, but we have not given its name. Top crossing C crossing TE mode instead of TE. Okay. Now we go for the TM mode simulation. I'll just stop sharing this one. Go to key layout, press F, this window, key layout. So moving to TM mode. So first of all, I have to control. This is F. Let me delete this laser here. Tell photo detector, photo detector, photo detector. Now I have to put laser here. Now this time it should be TM mode. So this should be 2. And this is the laser. And after that photo detector. So again this will be up one is 1. And now this time it is anti-clockwise. 1, 2, 3. 1, 2, 3. Yeah. So what is the expected result is that maximum will be at available second one. Third one and third will not give more power. Photo detector So this will be 1 here. There it will be 2 here. And this will be 3 here. Skip. So the geogratic photo detector Q. Say photo detector number 2 and photo detector number Q. Photo detector number 3. Edit. Now go for the simulation. Circuit simulation. So it is available here. I want to show you. Stop this. Window. Second one. Actually, I'm not able to fully see. This is T. Why it is TE? Should be TM. Let me close first one. Yeah. Window TM. So now this is getting up to TM mode. So let us simulate it. Run the simulation and complete it. So as usual, by default, it is again. So right click, display the results. And now you can see this is here. Only one. Why cross it? What are the other ports? All ports are connected here. Result view. Okay. Ports. Simulation. Display result. Only mode 2 is giving the output. Rest are not giving. It means no output is available at all in this. Result view. Mode 2. Yeah, surprisingly. So you can see in TM mode. So port 1 and port 3 are not giving at all the output. A reasonable output which can be plotted here. However, port 2 is giving, this gain curve here. So from 1540 to 1570 is okay for that much gain. So we can save it as a TM mode. Crossing this TM mode. Crossing it. Yes. Save it. crossing. This should be crossing TM mode. TM. Yes. Save it. So with this we have seen T mode, some light was there, but TM mode not at all, only state waveguide light is coming. However, we see functional layout, what happened, labeling. Okay, it is a related OPT bit only, as usual last time. So with this, thank you so much for attending. We have simulated this crossing EB electron beam lithography process design kit. After that we have crossing. So we have seen that transmission loss 0.2 dB, less than 0.2 dB, and crosstalk and reflection less than 40 dB in broad bandwidth of 20 nanometer, supports both TE and TM mode. So you can see if light is coming from for TE mode, if light is coming through this, so maximum light is coming here, and this side is very less light for TE mode. And for TM, we can see light is passing input here, and maximum light is available here, but no light is available here in these two ports. Okay, so thank you so much for attending this session. Thank you so much. Stop.